Fixing mistakes in predictions with SongExplorer. In this video, I'll demonstrate the workflow used to iteratively add annotations to a set of existing ground truth data. As accuracy is improved most by annotating sounds for which the predictions are incorrect, we'll first cluster the predictions on a new recording and annotate the false alarms. Then we'll cluster detected sounds which have no corresponding event in the ethogram and annotate the misses. As before, the commentary will be brief, and much more detail can be found in the written documentation over here. First, click on the Fix False Positive wizard. We'll start with a previously trained classifier. That's been used to make predictions on a recording that we haven't annotated yet. Make sure that wanted words and label types are sign, pulse, ambient, and other, and annotated and predicted, respectively. These two fields should be automatically filled in when you click the False Positives wizard. The first action is to send all the predicted events through the forward pass of the model and save all the input, hidden, and output layer activations. Again, recall that gray is that the action is pending, black is that it's actively running, blue that it's successfully completed, and red that there is an error. Proceeding left to right in the row of action buttons, we go to Cluster, choose just the final hidden layer, and activate the Do It button. Any activations and cluster files that previously existed in your ground truth data will be overwritten. Finally, we visualize these clusters. Make sure to select the final hidden layer. And under Kind, we want to look at Predicted. Note we have 3 clusters here that are very well segregated. The colors indicate what their predicted label was. We can look at each separately. To fix false positives, we want to simply examine all the predictions and make sure that they are correct according to our eye. Here, for example, this cluster is all the pulses. Again, this is Drosophila melanogaster song. Nominally, everything displayed in this little snippets panel should look like a pulse. Clearly there are some things that don't. You want to focus your effort on fixing the obvious mistakes that are clearly an error. You can see here how true sine song and the interpulse interval are nicely segregated into two clusters. It's very common for interpulse interval to be thought of as sine by a classifier that has only been trained on sine, pulse, and ambient. For the time being, we won't address that issue. Possible workarounds are to create a new label called IPI, and you can either manually annotate that or programmatically create new annotations by simply inserting an IPI label between every pair of pulses. Once you have fixed all the obvious false positives, it's time to correct misses. Click on the Fix False Negatives wizard and detect sounds in this recording. The thresholds used in the time and frequency domains are again down here. A detected CSV file is created. Which looks like this. We then do the misses action. The misses action wants as input the detected and the predicted CSV files. It's going to then do some interval math where it looks for regions in time for which a sound has been detected, but no prediction exists. Output is a missed CSV file. Same format as the detected and the predicted and the annotated CSV files, but the fourth column indicates that these events have been missed. And the label is other. Now we pass all these missed events through the forward pass of our model and save all the input, hidden, and output layer activations. Again, make sure that wanted words and label types have been set appropriately by the Fix False Negatives wizard. In particular, you should have missed in the label types. And then we cluster as before, the hidden layer, using a two-dimensional UMAP. Note that there are 2,000 missed events in this file. At last we visualize. The kind we want to be missed. And as with fixing false positives, we simply search this space for events which are very good examples of words that we care about. Like this one, for example, appears to be a pulse, and yet it was completely missed by the classifier. So we just lay down a pulse annotation right there. Since we're here, we can also label that one, and might as well get this one too. Remember, you can change the size of the circle over here. If there are more than 100 events within that circle, only the first 100, this is a 10 by 10 grid, will be displayed closest to the center of the circle. Maybe this one's not so obvious, so we should leave it be. I'm just going to keep going until we get roughly 100 new annotations. Trying to sample them across this entire cluster space. That's 100. So let's go back and make predictions again on a new recording. First, we train another model using these new ground truth annotations. Inside this log file, you can see how it's divvied up the annotations between the validation and the training data set, as well as what the model architecture is, 2 convolutional layers and a dense layer with kernel shapes like this, and then a log of each step and a confusion matrix along the way. We'll now quantify those accuracies, make plots out of them. So across our 200 steps, the loss decreases and the accuracy, both the train and the validation, rise to around 90%. We'll now freeze this model so that we can use it to make predictions on a new recording. But you can see I forgot to update the checkpoint file. So we'll do it again. This is a different strain of melanogaster, so we'll see how well it generalizes our model. Classify button results in sine, pulse, and ambient wave files that contain the probabilities over time of the occurrences of those 3 words. Here's the raw waveform. So, pulses have high probability there. Sine song, the sine channel is high and steady. During quiescent periods, the ambient channel, high and steady over here too. So it looks pretty good, even though it's a different strain. The last step then is to discretize those probabilities into an ethogram. the specific thresholds used, again, are in these thresholds files, which are created by the accuracy button, and they're calculated using a precision recall ratio of, in this case, 1 on the validation dataset. So in this case, when the probability exceeds 0.996, we're going to call that a sine. 0.993, we'll call it a pulse. 0.985, we'll call it ambient. And that will make, on the validation data set, the false positive and false negative rate, the ratio of those two equal to 1. As many false positives as false negatives. And here's that predicted CSV file. The output of ethogram is simply another CSV file where the fourth column is predicted instead of detected, missed, annotated. So that's it. I hope you enjoy SongExplorer.